We left off on number 10. So number 10 says use prime factorization to simplify the square root of 40x to the fourth y to the eighth power. Okay, so prime factorization means we're going to break down our number 40 into its prime factors. Factors means multiply. So 40 we know is 4 times 10, and 4 is 2 times 2, and 10 is 5 times 2. Now, if you're thinking, I want to do it a different way, I think 40 is 2 times 20, and I think 20 is 2 times 10, and I think 10 is 2 times 5. If you notice, this is the exact same prime factorization, 2 times 2 times 2 times 5, 2 times 2 times 2 times 5. Either way we do it, we're going to be looking for pairs, a group of 2, of our prime numbers. So we have a group. I'm just going to work with this one. I'm going to erase this. And then I have 5 and 2 are leftovers. I'm going to do the same thing with my variables. So I have x to the fourth, 1, 2, 3, 4, y to the eighth. So I'm looking for groups of 2 again. 1, 2, 3, 4, 5, 6. Okay, so I have a group of 2s. I have 2 groups of x's, and then I have 4 groups of y's. What I'm left over with is a 5 and a 2, and 5 times 2 is 10. When we are looking at simplifying radicals, we don't always have to have an even number of x's. If we say had x to the fifth power, we would have had one more x, and then we would have left it inside with the 10 because it wouldn't have had a partner. What we're looking for here is perfect squares, because x and x is really x squared. X and x is really x squared. So when we square root x squared, we just get x. We've got 2 of them, so x squared. Number 11. This denominator is all equal to 1 because anything to the 0 power is 1. So we just need to look at my numerator. 3 squared, 3 times 3 is 9. And using our power rule, 5 times 2 is 10. If we didn't want to use those shortcuts, we could always write this out. We have 3x to the fifth times 3x to the fifth. And 3 times 3 is 9. And then count up our x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's my answer. Okay, integer operations. -6 times -3 times +3. We all remember that multiplication can go in any order. So just to make this easier on my brain, I'm going to multiply the 3's first. So -3 times +3 is -9. And if I multiply -6 times -9, that's a +54. -12 divided by -3 is +4. Remember, if I have 2 negatives, then my answer will be positive. Now that trick only works with multiplication and division. For adding and subtracting, we have to keep, change. So we're going to keep, we're going to change this to a plus, we're going to change this to a plus. So -7 plus 4 is -3. We can also think of this as that these 2 negatives make a positive. These 2 negatives make a positive. Or we can keep, change. Number 14 is kind of an easy one. We're just going to multiply our coefficients. So 3 times 4 is 12, z, and then we have 4 z's and 2 z's. So if we write that out, we have 6. Adding our exponents while our bases are multiplying. Okay, number 15 is prime factorization again. So 250 is 25 times 10. 25 is 5 times 5. 10 is 5 times 2. Again, if you wanted to do this a little bit differently, you could say that 250 is 2 times 225. I'm sorry, 125. And you could continue to break that down. So 125 is 5 times 25. And then 25 is 5 times 5. Either way, you're going to get 3 5s and a 2. So again, we're looking for that group. And then these are our leftovers that are going to stay on the inside multiplied together. Now, if it happens that you have two groups, let me show you another example. So let's say 54. That's two. No, that's not going to give me what I want. Let's say 120. So that's 2 times 60 and 2 times 30 and 3 times 10. No, that's not going to do it either. Let me do 240. That should work. Just trying to get it to come out how I want it. Okay, so that's 24 times 10, 6 times 4, 3 times 2, 2 times 2, 5 times 2. Okay, so I have a group of 2's here and a group of 2's there. So 2 times 2 is 4, and then my leftovers are the 5 and the 3, so that's going to give me 15. So do you see how that part's different? So if you have two groups, like a group of 2's and another group of 2's, they multiply on the outside to give you 4. And then my leftovers are going to multiply on the inside to give me 15. Now, when I say things that are left over, don't tell me that 10's left over, because 10 was composite. 10 is a composite number. It's broken down into 5 and 2. We're only looking at prime numbers. They have to be in the ends. Prime means its only factors are 1 and itself. Okay. In number 16, both variables have negative exponents. So my p to the negative 8 is going to come down to the denominator and become positive. And my p to the negative 2 is going to come up to the numerator and become positive. So 49 divided by 7 is 7. And then in the numerator, we have p to the second. Denominator, we have p to the eighth. Using my subtraction rule, 2 minus 8 is negative 6. So I'm going to leave that 6 in the denominator as positive. If you need to see that written out, 2 p's in the numerator, 8 p's in the denominator, cancel. How many are we left with? 6. Where? Down in the denominator. This next one's a little bit tricky to think about. So what we know is that we are left with something in the denominator. So we have 2 7's in the numerator. Then we don't know how many we have, but we know that we're left with 5 7's down in the denominator. So the only way we're going to get them down is if they're negative. So think about if I put some 7's down here. What would happen if I put 2 of them? They'd cancel out. We wouldn't be left with anything. So how can I ensure that I'm actually left with 5? How many would have to be down there if I canceled 2 of them out? 7. But the 7 7's are in the denominator. So that makes this a negative 7. A quick way to check my work is to use that multiplication rule. If my bases are the same, I add my exponents. What's 2 plus negative 7? It's negative 5. And that's why I have a 7 to the 5th power in the denominator. Okay, volume. We're just going to take our length, our width, and our height and multiply them together. We are going to multiply our coefficients. So 5 times 4 is 20. We will add our exponents. 7 plus 3 plus 5 is 15. And to be 100% correct, that would be units cubed when we have a volume, because this is a 3-dimensional shape. So in number 19, we are trying to see who did this right. Is it Taylor? Is it JT? Who was correct? So really the only difference is this x squared supposed to be positive or is it supposed to be negative? So where did this come from? Well, in the original problem, we had an x to the negative 2 in the denominator. So when both of these people looked at this problem, they knew that they had to bring the negative up into the numerator. But what Taylor didn't do correctly is when she brings the x to the negative 2 power up into the numerator, she is supposed to make that exponent positive. And then 3 plus 2 gives us 5. So JT would be correct because negative exponents in the denominator equal positive exponents in the numerator. In other words, when you bring your negative up from the denominator, it should be positive. Okay, last one. I'm not going to write this out. I would have to write C 1, 2, 3, 4, 5, 6, 7. I would have to write that 4 times. 1, 2, 3, 4. You can see if I wrote out C that many times, how many would I have? What's the shortcut? I'm going to multiply my exponents. 7 times 4 is 28. Good luck. Study, study, study.